The main focus of this screencast will be to consider the collision theory and the vocabulary, graphs, and math that goes with it. So imagine we were in the classroom and I'm standing and I'm holding a soccer ball. And you are over here and you want to receive this soccer ball and catch it. We would call that an effective collision should I throw the soccer ball to you and you were able to catch it. Now, it is possible that I could throw it with not enough energy. If I didn't throw it with enough energy, you would not be able to catch the soccer ball, and that would not be an effective collision. And again, here we're thinking of the soccer ball as being a particle and you being a particle. Now, let's imagine that I throw the soccer ball with too much energy and it went right through you. In other words, the one particle destroyed the other particle. Well, if this was a real soccer ball and I actually did this, you would hate it if that happened. But imagine that I threw that soccer ball with just the right amount of speed and you were able to catch it. That would be an effective collision. But there's another possibility. Imagine that I was going to throw the soccer ball and this time you're facing the other way. Okay, you're facing and you're looking that direction. So if I threw the soccer ball at you, it would hit your back or head or something and fall down on the ground. That would also not be an effective collision, even though I threw the soccer ball with enough energy. And the reason for that would be that your orientation in space was not optimal to be able to catch the soccer ball. So there is a position you need to be in three-dimensional space, and this would be true of both particles actually, for the collision to be effective. This lays the foundation for understanding the collision theory of reaction rates. So, a quick review, since we're looking at this at the atomic or molecular level. Remember, the particles that we think about are either atoms, ions, or molecules. That's what we're aiming for, when we think in terms of the kinetic molecular model. That the speed of the chemical reaction is going to be important, and the orientation in space is going to be very important for the collision to be effective. Now, the speed, there's going to be wide differences. As we've said before, you can have an explosion very, very fast, or say out in the desert, you could have rusting that might take years. Also, you know that if you increase the temperature, then the reaction speed is going to also increase because the particles will have more kinetic energy and be moving faster. Another thing that's important is the concentration of your reactants. Just like there's more collisions during rush hour traffic than on a wide open, practically barren interstate in Montana, because the concentration of cars is so great. The same is true in a reaction environment. The higher the concentration of reactants, you can expect the reaction rate to increase. All of this plays into what we call the collision theory. So here's three parts to this collision theory. We are assuming in the collision theory, that the reacting molecules must collide with one another. Now, collision doesn't necessarily mean they have to physically touch, of course, but come close enough for there to be an interaction. That they must have enough energy. I have to throw the soccer ball with enough energy, just the right amount, because that's what's necessary to break and form bonds. And then the orientation of the particles must also be correct. In my illustration with the soccer ball, you can't have your back turned. So, when we continue on, we see that it's very reasonable, logically, using this model of particles that we have in our mind, that the rate of their reaction, how fast it takes place, the number of particles per period of time, the rate of change in the concentration of reactants, we could represent that by this, will be related to the number of collisions, and that, of course, is going to be a function of what their initial concentrations, or in my illustration here, the molarity, happen to be. If it's a first-order reaction, you double the concentration, and you expect to double the rate, because you expect to have twice as many effective collisions. They would be directly proportional. Now, the collision theory, back to thinking about the temperature and the reaction rate. You cool things down, you usually slow down the reaction. You warm things up, you usually increase the rate of the reaction. And chemists have studied this substantially. You should also remember from an earlier page in chapter 11, the Boltzmann distribution energies. That curve looks something like this. It's not a bell-shaped curve because you'll notice the end tapers off and becomes horizontal, either at 0 or someplace above 0. That's called a Boltzmann distribution curve. Now we have some vocabulary words to go with this. First of all, the molecules need to have a minimum energy to react, just like with the soccer ball that I threw at you. I have to throw it with enough energy to actually get to your hands. We call that barrier, that amount of energy that you have to exceed, as the activation energy. And sometimes you see it written with the A right here, and sometimes you might see it written with a little circle. This is the activation energy, the energy required before the reaction can proceed on its own. If the activation energy is low, in other words, if there's a low barrier, then you expect there to be a lot of effective collisions because a lot of particles have sufficient energy. And therefore, this reaction ought to be fast. If your barrier is high, that's a high threshold, so to speak. Not very many particles might actually have that much energy. Therefore, there's not going to be as many collisions. Therefore, this reaction should be slow. And a typical model that I've seen used in many, many chemistry books is somebody hitting a volleyball. You can think about the difference between playing tennis and playing volleyball. The amount of energy, at least potential, vertical energy, that the tennis ball has to have isn't that much in order to get over the net because the net is low. The volleyball has to have a lot more because it's high. It's just like shooting a basketball. If the rim is down at 8 feet, then maybe kids in kindergarten, first grade could probably make a lot more baskets. But if things continue to go where people are taller and taller, pretty soon you could have a whole team of 7+ footers, and you might want to raise the rim maybe to 11 or 12 feet, just to make things more interesting. The basketball would need more energy to get that high. Now, as soon as you reach the top of the curve, we call that the reaction coordinate. And before we proceed on that, let's take a look at these Boltzmann curves that you've seen before. Notice that temperature is a function of the x-axis and not a function of the y-axis, as we often think about. This is temperature, not time. Because temperature is a function of the kinetic energy. or the way that I like to designate kinetic energy is like that. And that, of course, is 1/2 mv squared, where the energy is a function of that velocity. So this is going to be the number of molecules that have a given energy. Some molecules have very, very low energy, way down here on the y-axis. And other molecules also have a whole lot of energy, but not many of them as well, because again, it's way down low on the y-axis. Most of your particles are going to have some amounts of energy well above that, including a few that are going to have, you're going to have a particular energy value right here, where you have your most particles with that much energy. Excuse me again. So, let's imagine that the activation energy necessary for a particular chemical reaction to take place is this barrier right here. You have to have this much energy for the reaction to take place. So all the particles over here don't have enough energy. They're soccer balls that don't reach you. These particles over here would be soccer balls that do reach you. They have enough energy. Now, the other thing you should notice is that at my lower temperature, these are the only particles that have enough energy. But if I raise my temperature to a higher temperature and look at how many particles have enough energy, not only do the particles represented by the area shaded in blue, but now the particles represented by the area shaded in gray all have sufficient energy for there to be an effective collision, should the orientation be right. In other words, raising the temperature from here to here, raising that temperature increases the number of particles that have sufficient energy. Now that energy, when you get to the very, very top, come back to this graph, this energy right here, there's your activation energy needed at the lower temperature, but at the higher temperature you don't need quite as much energy. You're going to get a lot more particles. I'm going to erase this and use a different graph to explain that better. I think it's coming up. Yeah, here we go. This is what I'm looking for. So, in this case, we do switch the axes. So now in this case, the y-axis is where I have my energy. Yeah, that makes a lot more sense. And my reaction progress, in a sense, we could say that's a function of time, how far along the reaction is. Imagine that I have my reactants with a certain amount of energy right here. I'm going to designate that as E sub R for the energy that my reactants have. Now, if I give it some energy, this is the activation energy. Here's my activation energy, E sub A. Now my particles have this much energy. I've added energy to the energy they already had as reactants. And at this point now, the reaction can proceed on its own, left to right. And finally, we get down here, which we could say is the energy of my products. Now, this point right here is called the transition state, where the reaction now transitions between needing energy to releasing energy and moving on its own. Now it becomes spontaneous at this point. And this is called, again, the transition state, an important vocabulary word. We sure would like to know what the particles look like at their transition state. You can't really take a picture there because it happens so fast. At this precise moment, you're at equilibrium. You could just as easily go that way as that way. This is often the mystery. What does it look like in between the start and the end of the reaction? Another thing you should notice is that whereas I started here, I ended down here. My particles ended up with less energy. And the reason it had less energy is because it lost energy to the environment. That energy that it lost went into the surroundings or the environment. And we call that, of course, exothermic. So this graph would be a picture of an exothermic reaction. The loss of energy from the reaction environment to the surroundings. And I'll say one other thing about this graph that I don't like, and that is it makes it seem like that the energy of your products is zero. And so, just to be clear, this value right here, as far as the y-axis is concerned, is not zero because it's impossible for these particles to have zero energy, the particles of the products. That would require a temperature at 0 Kelvin, which you can approach but not achieve. And since we're seldom dealing with reactions that are that cryogenic, low temperature, we have to remember that in this graph, it does not go to 0 on the y-axis. Now you might say, well, what would a reaction look like for an endothermic reaction? And hopefully you see it would look something like this. There's my transition state. Here's my activation energy. Here's my energy of reactants. Here's my energy of products, right about there. You'll notice that we're increasing in energy. This would be endothermic. We could also say that for a reverse reaction, and maybe I need to go to a different color for the reverse reaction. The reverse reaction, if we were going to go in this direction, this would be my activation energy for the reverse reaction. Whereas over here, this would be the activation energy in the reverse direction. I did that backwards. It's E sub A. So imagine if we took the graph on the left and held this corner of the paper solid and flipped it over onto its back, then you would have this graph on the right. And here's an actual example of a coordinate diagram for a two-step reaction. The first step takes us to this point, and the second step takes us to this point. So you have two humps. And you have your initial activation energy to get to the first transition state, and then you have another activation energy to get to the next transition state before the reaction can proceed on its own. So in a sense, you have two reaction intermediates. You have whatever the configuration is at that point and whatever the configuration is at that point. And as we said before, raising the temperature increases the reaction rate because it means that there are more molecules, a higher percentage or fraction of molecules that now have enough energy to get over that activation energy barrier. In a sense, we could say that we've lowered the mountaintop. If this is how much energy we need right there to get over the top, maybe some alternate mechanism or a catalyst means all we need is this much energy. We've chopped off the top of the mountain, or maybe we've gone around the side of the mountain. We don't have to get quite as high for the reaction to proceed on its own. Now, mathematically, what's this going to look like? Well, for that, we have the Arrhenius equation. Savante Arrhenius. I think we've mentioned him before. A little over 100 years ago, if I remember. And this equation shows all the things that would go into determining what our rate constant is. Remember that the rate depends upon my initial concentration and the temperature. There's your temperature, okay? It also depends upon what the collisions are going to be, how often they're going to collide, which would be a function, for example, of its concentration. It would depend upon what kind of activation energy you need. And you'll notice your constant, often called the gas constant, but it also holds true for particles moving around even in a solution. So all of these things go into what we call the Arrhenius equation. And it's a nice equation, maybe not in this form. We're going to change its form in a little bit to make it a little bit easier to use. But it allows us to calculate what the activation energy is, which is not always easy to do, especially since, again, if I draw the graph, we know where you start and we know what the energy is when you end, because they'd be a function of temperature. But we don't necessarily know what that energy is at the top, which means we can't find the activation energy. But this equation will allow us to do that. It can also help us to find the rate constant, K. So if we put it into a form, if we take the natural log of both sides of that equation, and then algebraically manipulate it a little bit, we get this equation right here, the Arrhenius equation. So where I am on my y-axis, that's the natural log of my constant. And if I wanted to find the frequency factor, that's where it crosses the y-axis, the y-intercept. My x is the reciprocal of the temperature in Kelvin. And then my slope of this line, a straight line, would be the activation energy divided by R. And since R is a constant, all you have to do is take your slope and you multiply it by R, and you have the activation energy. The negative sign, of course, tells us that we're going downhill, because the number of my reactants is diminishing as time goes on. And here's an example of using the Arrhenius equation. You are given 4 experiments here. You can pick any 2 experiments. You can look at this temperature difference and this K difference, or this temperature difference and this K difference, or this temperature difference and this K difference. Doesn't matter. You have all those different combinations. Just make sure you're consistent. Use the same 2 temperatures that correspond to the same 2 Ks. Then you can graph that equation. And on graphical analysis, you could do the stat box. So you'll have a stat box here, and in the stat box it'll tell you what your slope is. And once you know what your slope is, you can use since your slope is this, you can use that to find your activation energy. And of course, your activation energy ought to be positive, because it's energy you have to put into the system in order to make the reaction proceed spontaneously on its own. Let's see. Here's another variation of that equation. And now we're going to wrap things up by looking at the effect of catalysts on reaction rate. Now, when I ask you on a test, or anyone else does, if Al-Qaeda does, what is a catalyst? Your answer better have two parts. Part one, it speeds up the chemical reaction. Remember, enzymes are biological catalysts. But number two, it's not consumed in the process. It's not used up, which implies that you can use it over and over and over again. Now, enzymes, biological catalysts, because they are organic and generally more fragile, if you will, than inorganic, there's a limit to how many times you can use it. It might be thousands or more than that, but still there would be a limit. So, because of the high activation energy, if you've got a high activation energy, you're going to have a slow reaction, which would imply you need a catalyst if you want this to go faster. If it was a very, very low activation energy and it's going too fast, you would probably need to have some type of compound that might slow it down. We often call that an inhibitor, to inhibit the reaction, to make the speed more manageable. How do these catalysts work? We don't always know. There are labs around the world looking through thousands and thousands of chemicals, both synthetic and naturally occurring in the environment, trying to find new catalysts that might be cheaper, or catalysts that might be greener, better for the environment, or catalysts that might be safer, meaning not as toxic, for example. There's all kinds of reasons for looking for these catalysts. Many reactions we don't have a catalyst for. But how the catalyst actually works is often a mystery, because as we've said, what's happening right there at the top, we don't always know what that is at that transition state. All we know is we've got to change that transition state. And that often involves changing the mechanism, which, by the way, is the main focus of the next screencast that you have available to you. Talking about the mechanism. Remember the Nassau clock reaction, where the mechanism obviously involved the formation of something golden in between when you started and when you ended. So a lot of times in these mechanisms that we propose, if it's multiple steps, you might make a compound in an early step, and then in a subsequent step, that reaction intermediate, which might be a product in an early step, turns around and becomes a reactant in a subsequent step. It's here today and gone tomorrow. It's made in one step, used up in the next. That's called a reaction intermediate. And the reaction that they're talking about in this example uses iodine as a catalyst. Now, remember, catalysts don't show up in your stoichiometry. It does not appear when you write your balanced equation of reactants turning into products, but it does appear in the rate equation. It does appear in the rate equation because it affects the rate. And the rate equation is a reflection of the reality for it to be true. And a vocabulary term, if it happens to be in the same phase or state as what's reacting, we say it's a homogeneous catalyst as opposed to a heterogeneous catalyst. And so when we use a catalyst, instead of a energy profile that looks like this black line here, instead we might get one that, because we've changed the mechanism substantially. We might get a initial activation energy, and then we need another one, and then perhaps another one that happens to be the same or maybe not, and then another one over here, and so forth. And as a result, we have multiple humps, each hump representing a different step in the chemical reaction, a step in the mechanism. And so instead of needing to get all the way up here in terms of energy, let's say somewhere around 350 kilojoules per mole, now ultimately we only need to get somewhere here, let's say maybe 125 kilojoules per mole, substantially less. And so the reaction can go a lot faster, even though it's more complicated. In fact, that speed could increase by this factor right here, 1,000 trillion times faster. So we just went from a one-stepper to a multiple stepper. And just for the record, if you have a three-step reaction, it is not called a waltz. Teacher joke, just to see if you're awake. All right, next screencast we'll talk about reaction mechanism.